All right, so here's the question. We're going to determine all the complex zeros of this polynomial function. It's a fifth degree. Remember, complex zeros would include all rational, all real, which is rational and irrational, and all complex, which would include the imaginary numbers. So according to the fundamental theorem of algebra, there should be exactly 5 of these because it's a fifth degree. So first of all, the rational zeros. The rational zeros, as we know, are in the form P over Q, where P is all the factors of 4 and Q is all the factors of 1. And if you do all combinations P over Q, you get plus or minus 1, plus or minus 2, and plus or minus 4. So if there's any rational numbers, they have to be from this list of 3. So what I'm going to do here is I'm going to graph this and kind of cheat, find out which one should work. So I did graph it already, and you can see on my graph that it looks like I lost my graph. It looks like negative 1 and 1 are the rational zeros. Furthermore, negative 1 bounces. So negative 1 should happen twice. And here's 1, it goes through. So that happens only once or 3 times. We don't know. It just goes through. But from what I can see on my graph, I know negative 1 is going to happen twice at least, and 1 is going to happen once. So from here, I'm just going to run it through run all these zeros through synthetic division. So we have negative 1 twice, and 1 once, just to remind myself. So here we go. Now let's set this thing up. Let me get rid of all this stuff that's in the way. I'll start out with my synthetic division, negative 1 first. I have 1, 3, 5, 1, negative 6, negative 4. I should run that through. I should get 0 at the end. So let's do it. 2, negative 2, 3, negative 3, negative 2, 2, negative 4, positive 4, perfect. So negative 1, that was once. Since it bounced, it should happen twice. So continue along. And again, not surprising, that worked. Also, 1 should work. So I'm going to continue along. Uh-oh, that's a 4. So you can make mistakes here, but because we know what's going to happen, we're good. We'll find those mistakes really quickly. So we start out with a fifth degree. So each synthetic division, as long as you stack them, knocks it down a degree. So the final polynomial down here is a quadratic that we can handle because you can handle all quadratics. So I have 3 zeros already. I can solve this by factoring with the quadratic formula. To get my other 2 zeros, it's not going to factor. So the quadratic formula will give me x equals negative b plus or minus b squared minus 4ac all over 2a, which is 2 times 1. So I have negative 2 plus or minus 4 minus 16, which is negative 12, over 2. Simplify. Square root of negative 12 will simplify into I root positive 12. Now, square root of 12 is 4 goes into 12. It's a perfect square, so I'm going to do that. And simplify. The square root of 4 is 2. And finally, I'm going to split my fraction apart, negative 2 over 2, plus or minus 2I root 2 over 2. And it simplifies into negative 1 And these 2's will cancel here. Plus or minus, oops, I made a mistake. I see that right now. That's a root 3 in there from here. So plus or minus I root 3. So my 5 zeros, and I should have 5 zeros according to 5 complex zeros according to the fundamental theorem of calculus. Fundamental theorem of algebra. I'm in the wrong class here. X equals -1, multiplicity of 2. So that's 2 of them. X equals 1. There's your third. X equals -1 plus I root 3. And the last one is x equals -1 minus I root 3. Those are called complex conjugates. Complex zeros always occur in conjugate pairs, as we know. So we do have 1, 2, 3, 4, 5 complex zeros. I'm going to quickly check the complex ones, and I want to show you that an easy way to do that is on your calculator. We already have checked the other two because those came up from the graph, but it's hard to check the complex ones. But you can if you go. One of the ways I've found it to be kind of easy is type the function in on the calculate screen, and if you just do that, it's not going to do much for you. I'm going to hit enter, but let's plug in one of these complex numbers for x. So I'm going to use -1 plus I root 3. So what you can do is this, -1 plus I, which is above the second decimal point, and then root 3. If this is a 0 and you plug it into this equation up here, it should become 0. So it's hard to do that, but I'm going to store this in for x. So my calculator now thinks that this is x. So now if I type this equation in again, it will automatically substitute that -1 plus I root 3 in for x, and I should get 0 if I'm right, because it is a 0. And I do. So now I can check the other one, which is going to work because you know if it's a complex conjugate, but I'm just going to make sure. I'm going to change this now to minus. Now that's what's stored in for x. So now if I plug this equation in again, I should get 0. And I do. So that checks it. And if you just if I put -6 in for x, this should not work because 6 was not one of my zeros. So if I did change that x to 6 and type this, I should not get 0, and I obviously don't. So that's your check. It's pretty simple. So practice that.